Black holes swallow everything. Light can't escape. Matter vanishes forever. We built physics around that certainty. Then, in 1974, a Cambridge physicist named Stephen Hawking proved black holes die. They radiate. They evaporate. They explode. The mechanism that kills them is stranger than anything in science fiction, and the timeline is so vast it makes the age of the universe look like a blink. But the real twist isn't about time. The reason black holes eventually evaporate involves quantum ghosts, violated laws, and a temperature paradox that flips everything we thought we knew. Stand at the edge of a black hole event horizon, the boundary where escape velocity hits light speed. Cross it and you're gone. Physics says nothing returns. But right there at that invisible line, something impossible happens. Empty space isn't empty. Quantum mechanics proved that in the early 20th century, the vacuum seethes with particle pairs popping into existence and vanishing before you can measure them. An electron appears with its antimatter twin, the positron. They exist for a trillionth of a second, then annihilate back into nothing. Heisenberg's uncertainty principle allows this. Energy can be borrowed from nothing if you pay it back fast enough. The time frame is tiny. About 10 to the negative 43 seconds. That's the Planck time, the smallest meaningful tick of the clock. Now put that quantum foam near a black hole horizon. September 1973. Stephen Hawking met Soviet physicists Yakov Zeldovich and Alexei Starobinsky in Krakow, Poland at a cosmology meeting. They told him rotating black holes should emit particles by stealing rotational energy. Hawking went back to Cambridge thinking they were wrong. He ran calculations to prove it. 4 months later, in early 1974, he found the opposite. All black holes radiate, not just spinning ones. Even a perfectly spherical, non-rotating hole emits thermal radiation. He thought he'd made a mistake. The numbers kept coming back the same. Black holes have a temperature. On March 1st, 1974, Nature published his paper, Black Hole Explosions. 2 pages. The equation that emerged became his most famous work. Temperature equals h bar times c cubed divided by 8, pi times g times m times Boltzmann's constant. In plain terms, the temperature of a black hole is inversely proportional to its mass. A solar mass black hole sits at 60 nanokelvins. That's 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background at 2.7 Kelvin. It actually absorbs more radiation from space than it emits, but flip the mass down and watch what happens. If you value documented physics and quantum mechanics history like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. Also, this script is researched and factual using sources from the Journal of Cosmology and Astroparticle Physics, published May 12, 2025, by Heino Falke, Michael Wondrak, and Walter van Zuilicom at Radboud University in the Netherlands, showing space-time curvature alone causes evaporation even without an event horizon. And Communications in Mathematical Physics, Volume 43 from 1975, where Hawking published his full mathematical treatment proving black holes emit particles as if they were hot bodies. Now back to the information. A black hole with the mass of Mount Everest would measure about 1 millimeter across. Temperature climbs to billions of Kelvin. It glows white hot. One with the mass of an asteroid roughly 10 to the 12 kilograms has a Schwarzschild radius around 10 to the negative 15 meters. Nuclear scale. Temperature jumps to 10 to the 12 Kelvin. Trillion-degree heat packed into a space smaller than a proton. These aren't theoretical toys. They could have formed in the early universe, primordial black holes. Density fluctuations in the first fraction of a second after the Big Bang could have crushed pockets of energy into microholes. Any primordial black hole with initial mass below about 5 times 10 to the 14 grams would have fully evaporated by now. 1976. Don Page at Caltech refined Hawking's numbers. He calculated evaporation timescales as the cube of the solar mass black hole takes 10 to the 67th years to vanish. The current age of the universe is about 10 to the 10th years. You need 10 to the 57 universes stacked end to end in time to watch a sun-weight hole disappear. Page also calculated the Page time, the moment halfway through evaporation when something critical shifts. The black hole has radiated half its original mass. The entropy curve hits a peak, then turns downward. Information that fell in starts coming back out encoded in the radiation. That's the theory. Proving it is the fight. The popular explanation for how Hawking radiation works is wrong. Hawking himself gave us the flawed story in A Brief History of Time. Virtual particle pairs appear near the horizon. One falls in, one escapes. The black hole loses mass equal to the escaped particle's energy. Clean, visual, totally misleading. The actual mechanism has nothing to do with particles splitting at the horizon. It's about quantum fields and curved space-time. Two different observers measuring the same vacuum state disagree on what counts as a particle. Someone far from the black hole in flat space sees a vacuum. Someone near the event horizon in strongly curved space sees particles. The mathematics involves Bogoliubov transformations. You take the quantum field solutions from before the black hole formed and map them to solutions in the warped geometry around the hole. Positive frequency modes that represented no particles in flat space turn into mixtures of positive and negative frequency in curved space. That mixture looks thermal. It radiates. Physicist John Baez at UC Riverside emphasizes, nobody has worked out a proper local description of Hawking radiation at the horizon itself. The calculation is global. It compares distant past to distant future. The virtual particle picture is a cartoon, useful for intuition, incorrect for physics. Here's what actually drives the process. Space-time curvature creates a difference in the quantum vacuum state between regions. Near the hole, gravity is strong. Tidal forces stretch space. Far from the hole, space is nearly flat. The quantum field has a different ground state in each region. The difference in vacuum energy produces real particles. Think of it like the Schwinger effect, but with gravity instead of electric fields. Place a strong enough electric field in empty space, and it rips a particle-antiparticle pairs out of the vacuum, making them real. The field energy pays the cost. For black holes, the gravitational field does the same thing. June 2nd, 2023. Physical Review Letters. Volume 130, published findings from Michael Wondrak, Walter van Swellicom, and Heino Falke, showing gravitational pair production happens without needing an event horizon. The curvature alone is enough. Tidal forces separate the particle pairs. One escapes, one doesn't. The energy comes from the gravitational field, which means it comes from the black hole's mass. Mass decreases, temperature climbs, the rate of emission accelerates. Runaway evaporation starts once the black hole shrinks below a critical size. Primordial black holes in the mass range around 10 to the 11 to 10 to the 15 kilograms, should be reaching the end of their lives right now. 14 billion years after the Big Bang, if they exist, NASA's Fermi Gamma Ray Space Telescope launched. June 11, 2008 was designed partly to hunt for them. The final burst from an evaporating black hole should release about 10 to the 30th ergs in the last tenth of a second. That's equivalent to 1 million 1 megaton hydrogen bombs detonating simultaneously. The radiation peaks in the mega electron volt to tera electron volt range, gamma rays, very high energy photons. Ground-based telescopes like Veritas, the Very Energetic Radiation Imaging Telescope, Array System and MAGIC, the Major Atmospheric Gamma Imaging Cherenkov. Telescopes scan for these bursts. They look for a specific signature. The burst should have a thermal spectrum matching the black hole's temperature, which changes rapidly as it shrinks. May 28th, 2024, research published in physics.org described how black hole morsels created during gravitational wave mergers might produce detectable gamma ray bursts with distinctive fingerprints. A morsel with mass around 20 kilotons evaporates in 16 years. Heavier morsels produce steadier signals at first, then explode. The Hawking temperature is inversely proportional to mass, so as the hole shrinks, the temperature and emission rate spike exponentially. No burst has been confirmed yet. That puts limits on how many primordial black holes exist. The local burst rate density in our cosmic neighborhood must be lower than detection thresholds. Some researchers calculated if primordial black holes made up all the dark matter in the universe, we'd see constant explosions in the sky. We don't. So either primordial black holes are rare, or the evaporation process works differently than predicted, or something about our detection methods misses them, or they don't exist at all. Each null result tightens the constraints. The Cherenkov Telescope. Array Observatory, CTAO, expected to come online fully in the coming years, will push sensitivity an order of magnitude better than current instruments. Energy range from 20 giga electron volts to 300 tera electron volts. If primordial black holes are out there, CTAO might catch one dying. September 1st, 2025, research on arcs of a detailed CTAO's prospective sensitivity, showing it could either achieve the first detection or set the most stringent upper limits on local burst rates. Now the temperature paradox. Black holes are the only objects in the universe that get hotter as they lose energy. Normal matter cools when it radiates. A star burns fuel, heats up, then cools as fuel depletes. A black hole radiates, loses mass, and heats up. The smaller it gets, the hotter it burns. Once a black hole drops below about 10 to the 23 kilograms, its temperature exceeds the cosmic microwave background. It starts losing energy faster than it gains energy from absorbing ambient radiation. Net evaporation begins. Before that point, the universe is too hot. The hole absorbs more than it emits and grows. This creates a feedback loop. Evaporation accelerates, temperature climbs, emission rate increases, more mass loss, higher temperature, faster evaporation. At the very end, when the black hole mass approaches the Planck mass about 2.2 times 10 to the negative 8 kilograms, or roughly the mass of a human cell, all bets are off. The Schwarzschild radius shrinks to the Planck length 10 to the negative 35 meters. Quantum gravity takes over. We don't have the equations. General relativity breaks. Quantum mechanics breaks. We need a unified theory. String theory loop, quantum gravity, some framework that merges gravity with quantum physics. Nobody has it yet. What happens in the final Planck time interval before the black hole vanishes is unknown. Does it explode in a burst of Planck energy particles? Does it leave a remnant? Does it tunnel into another universe? Open questions. If you value documented frontier physics like this, subscribe. Also comment from which city you're hearing this from. This script is researched using sources from Nature, Volume 2, 48 March 1st, 1974, where Hawking first published Black Hole Explosions, Predicting Thermal Radiation from Quantum Effects, and from research published in monthly notices of the Royal Astronomical Society, Volume 4, 33 May 12, 2025, by Falke Wondrak and von Swilecom, showing evaporation applies to all massive objects, not just black holes. Now back to the information. The evaporation time formula is brutal in its simplicity. Tau equals 5,120 pi times g squared divided by h bar times c to the fourth times m cubed. Lifetime scales with mass cubed. Double the mass and the black hole lasts 8 times longer. Cut the mass in half and it evaporates 8 times faster. For a solar mass black hole, plug in the numbers, 2 times 10 to the 30 kilograms. You get 10 to the 67 years. Modern estimates accounting for neutrino masses and particle physics details push that slightly higher, about 10 to the 67 years still, a supermassive black hole at the center of a galaxy. 100 billion solar masses. Evaporation time jumps to 2 times 10 to the 100 years. The monster holes that could grow to 10 to the 14 solar masses by swallowing galaxy superclusters would take 2 times 10 to the 106 years to evaporate. These numbers are so large they're meaningless in human terms. To put it another way, the current age of the universe is 13.8 billion years. That's about 4 times 10 to the 17th seconds. A solar mass black hole lives for 3 times 10 to the 74 seconds. That's 10 to the 57 times the current age of the universe. Stellar black holes are effectively eternal on any timescale we care about, but go small. A black hole with initial mass 5 times 10 to the 14 grams, about half the mass of Earth's moon formed at the Big Bang, would finish evaporating right now. The last second of its life releases more energy than the first billion years combined. The final burst is violent. Temperature reaches Planck scale, 10 to the 32 Kelvin. Radiation includes every particle the Standard Model allows, and probably particles we haven't discovered yet. Quarks, gluons, Higgs, bosons, gravitons if they exist. Everything. The spectrum is thermal, but the particle content depends on what masses are accessible at that temperature. A 1,000 kilogram black hole would evaporate in 10 to the negative 21 seconds. Blink and you miss it, except you can't blink that fast. Human blink takes about 1/10 of a second. This hole lives and dies in a time interval, a trillion times shorter. If the Large Hadron Collider at CERN could produce micro black holes by colliding protons at 13.6 tera electron volts, they would evaporate instantly. Hawking radiation would dominate. The hole would never grow. It would flash into existence amid a spray of particles and vanish. As of January 1st, 2024, none have been detected. Either the collision energy isn't high enough, or extra dimensions predicted by string theory don't exist, or black holes can't form at those scales. Temperature is the key to understanding why evaporation happens at all. Thermodynamics says anything with a temperature above absolute zero must radiate. Blackbody radiation. The spectrum depends on temperature. Hawking showed black holes have temperature, therefore they radiate. But temperature also connects to entropy. Early 1970s, Jacob Bekenstein, a graduate student at Princeton, proposed black holes have entropy proportional to the area of their event horizon. Not volume. Area, the formula. S equals k times c cubed times a divided by 4 g times h bar, where a is the event horizon area. Bekenstein couldn't pin down the proportionality constant. Hawking resisted the idea at first. If black holes have entropy, they have temperature. If they have temperature, they radiate. That contradicts the idea that nothing escapes. Bekenstein was right. Hawking proved it by calculating the temperature. The entropy formula became the Bekenstein-Hawking entropy. It says every Planck area on the horizon, roughly 10 to the negative 66 square centimeters, stores 1 bit of quantum information. A solar mass black hole with a Schwarzschild radius of 3 kilometers has a horizon area of about 10 to the 11 square meters. That's 10 to the 77 Planck areas, 10 to the 77 bits of information. Entropy is about 10 to the 77 times Boltzmann's constant. Enormous. The entropy of all the stars in the observable universe is negligible compared to the entropy of a single supermassive black hole. Here's where it gets strange. When you throw matter into a black hole, the entropy of the universe appears to decrease. The matter had entropy. It vanishes behind the horizon, gone from our universe. That violates the second law of thermodynamics. Entropy never decreases. Bekenstein solved this by showing the black hole's horizon area increases by more than the entropy that fell in. Total entropy still goes up. The generalized second law, S outside plus 1/4, the horizon area in Planck units never decreases. But Hawking radiation creates a new problem. As the black hole evaporates, the horizon area shrinks. Entropy decreases. That seems to violate the law Bekenstein just saved. The resolution is that the radiation carries entropy away. The total entropy of the black hole plus the radiation increases. The universe stays consistent. But there's a deeper issue. The information paradox. Throw a book into a black hole. The book contains information, the order of words on pages, the quantum states of every atom in the ink and paper. That information crosses the horizon. Now wait. The black hole evaporates via Hawking radiation. The radiation is thermal, random. It has no memory of the book. No way to reconstruct what fell in. The information is lost. Quantum mechanics says information is never destroyed. It's preserved in the quantum state of a system. You can scramble it, but you can't erase it. Unitarity. The evolution of a quantum system is reversible in principle. If you know the state now, you can calculate the state at any past or future time, using Schrödinger's equation. Hawking radiation seems to violate this. The black hole starts in a pure quantum state. It evaporates into a mixed state thermal radiation. Pure to mixed is irreversible. Information is lost. Paradox. Hawking spent 40 years wrestling with this. In 1997, he made a bet with physicists John Preskill and Kip Thorne. Hawking and Thorne said information is lost. Preskill said it's preserved. The stakes were an encyclopedia from which information could be recovered at will. 2004. Hawking conceded to Preskill. He presented him with a baseball encyclopedia. Hawking had changed his mind based on string theory arguments, suggesting information escapes via quantum correlations in the radiation. The community didn't fully accept his reasoning. The math wasn't rigorous enough. The paradox remained open. 1993. Don Page, working at the University of Alberta, made a crucial observation. Consider a black hole and its radiation as a single entangled quantum system. Initially, the black hole exists, and no radiation has been emitted. The entanglement entropy between the hole and the radiation is 0. As the hole evaporates, radiation escapes. The entanglement entropy grows. The radiation becomes entangled with the black hole interior. But if evaporation is unitary, if information is preserved, the entropy must eventually decrease back to 0 when the hole has fully evaporated. Plot entropy versus time. You get a curve that rises, then falls, shaped like an inverted V. This is the Page curve. The peak occurs at the Page time, roughly halfway through the evaporation lifetime, for a solar mass black hole that's about 10 to the 67 years in. At that moment, the black hole has radiated half its mass. The entanglement entropy reaches a maximum. After that point, information starts coming back out faster than it's going in. The radiation becomes increasingly correlated. The thermal randomness gives way to structure. The challenge was to calculate this curve from first principles and show it matches Page's prediction. 2018. Ahmed Almheri, at the Institute for Advanced Study in Princeton, laid out a procedure using concepts from string theory. The ADS-CFT correspondence. Anti-de Sitter space paired with conformal field theory, a duality that maps gravity in a higher dimensional space to quantum field theory on the boundary. Think of a snow globe. The universe inside is described by gravity and black holes. The surface of the globe is described by a quantum field theory with no gravity. The two descriptions are equivalent. Information in the bulk equals information on the boundary. If the boundary preserves information, so does the bulk. Almhiri and collaborators, including Netta Engelhart, Jeff Pennington, Henry Maxfield, and others, calculated the entropy of Hawking radiation by identifying quantum extremal surfaces in the bulk. These are surfaces that minimize a combination of area and entanglement entropy. The idea is that the entropy of the radiation is determined not just by the radiation itself, but by the minimal surface connecting the radiation region to the black hole interior. Early in evaporation, this surface lies outside the horizon. The entropy grows. At the page time, the surface jumps inside the horizon. An island forms. The entropy of the radiation includes the island inside the black hole. The total entropy starts decreasing. The page curve emerges. Papers published in fall 2019 showed this works in specific models. 2020 and beyond researchers, including Juan Maldacena, extended the results. Recent work in 2024 and 2025 continued refining the calculations for charged black holes in more realistic scenarios. The island formula says the entropy of Hawking radiation equals the minimum of two quantities. The area of the island boundary divided by 4 g times h bar plus the entanglement entropy of matter on the island, or just the entanglement entropy of the radiation without the island. Whichever is smaller wins. Early on, the no island answer is smaller. Entropy grows. At the page time, the island answer becomes smaller. Entropy decreases. The curve follows page. This is viewed by many as solving the information paradox. Information is preserved. It comes out in subtle quantum correlations encoded in the radiation. You need to collect more than half the radiation to start reconstructing what fell in. The information isn't lost. It's hidden in entanglement. But some physicists remain skeptical. The calculations rely on specific models. AdS space, not our universe, which is closer to flat de Sitter space. The AdS CFT duality is conjectural in full quantum gravity. No complete theory exists. The island formula works in the models, but does it apply to real astrophysical black holes? Open question. October 10th, 2024. Ethan Siegel, writing in Big Think, argued the information paradox still has been solved because we haven't changed how we calculate Hawking radiation itself. The fundamental process remains semi-classical. Quantum fields on a fixed classical geometry. A full quantum gravity theory is needed. May 12th, 2025 brought a new wrinkle. Radboud University researchers Falke Wondrak and Van Swylekom published in the Journal of Cosmology and Astroparticle Physics showing evaporation isn't unique to black holes. Any object with significant gravitational curvature emits Hawking-like radiation. Neutron stars, white dwarfs, even planets and people technically evaporate. The rate depends on density. For a neutron star, the evaporation time is 10 to the 67 years, same as a stellar mass black hole. For a white dwarf, it's 10 to the 78 years. For a human body, assuming only Hawking-like radiation and no other decay processes, 10 to the 90 years. The moon, 10 to the 90 years. These times are absurdly long, far beyond any practical relevance, but the principle matters. Evaporation isn't about the event horizon. It's about space-time curvature. The event horizon is just where the effect becomes strong enough to matter. The curvature generates tidal forces. Tidal forces separate virtual particle pairs, preventing them from recombining. One escapes. Energy comes from the gravitational field. The object loses mass. This applies everywhere. The effect is strongest near black holes because the curvature is strongest there. But it's universal. Everything decays. Given enough time, the universe will evaporate. The 2025 research calculated that stellar remnants like neutron stars and black holes of similar mass take the same time to evaporate. About 10 to the 67 years. White dwarfs last longer, 10 to the 78 years. The calculations assume an ideal environment with no external influences, no accretion of matter, no collisions, no background radiation above the object's temperature. In reality, most black holes grow more than they evaporate. They're bathed in the cosmic microwave background at 2.7 Kelvin. They're surrounded by gas and dust in galaxies. They accrete matter. Stellar mass black holes in binary systems can pull matter from companion stars. Supermassive black holes at galaxy centers devour gas clouds. Growth dominates. Only in the far future, after star formation has ceased and the universe has expanded and cooled below the Hawking temperature of the black hole, will net evaporation begin. That era lies trillions of years ahead. The universe is currently 13.8 billion years old. Stelliferous era ends around 100 trillion years from now. After that, the degenerate era, dead stars, black holes, dark matter if it exists, no new stars form. Black holes become the dominant remaining structures. They evaporate over timescales from 10 to the 67 years for stellar mass to 10 to the 100 years for supermassive holes. Eventually, the only black holes left are the largest ones. They evaporate last. The final black hole in the universe might be the supermassive hole at the center of a giant elliptical galaxy, mass 10 to the 14 solar masses, evaporation time 2 times 10 to the 106 years. After that, the black hole era ends. The dark era begins. The universe contains only radiation photons, neutrinos, maybe gravitons. Entropy continues increasing. The temperature asymptotically approaches absolute zero, but never quite reaches it. This is the heat death, maximum entropy. No free energy gradients, no structure, no life, no information processing. Just a cold, diffuse soup of low-energy particles spreading forever. Some cosmological models predict different endpoints. If dark energy causes accelerated expansion, the universe might rip apart in a big rip. If dark energy weakens and gravity dominates, the universe might collapse in a big crunch. If new physics kicks in, something else entirely could happen. But under standard cosmology, with a positive cosmological constant, the heat death scenario is the likely fate. And black hole evaporation is the final process that converts mass into radiation and maximizes entropy. Hawking radiation is the mechanism that closes the loop. Stars convert hydrogen into helium and release energy. That energy eventually spreads as heat and light. Matter ends up in black holes. Black holes evaporate. Everything becomes radiation. Entropy maximizes. The story ends. But the information paradox asks whether the story truly ends or whether information somehow persists. If information is fundamental to the universe, not just an emergent property, then maybe the heat death is the end. Maybe information encodes structure at levels we can't access. Maybe the universe is a quantum computer, and the final state is the output of the computation. Maybe the holographic principle is real, and the three-dimensional universe is a projection from a two-dimensional surface where all information is preserved. These are speculations. They go beyond current physics, but they motivate the work. Understanding Hawking radiation isn't just about black holes. It's about the deepest foundations of reality, how quantum mechanics and gravity fit together, whether space-time is fundamental or emergent, whether information is conserved absolutely or just probabilistically, whether the universe is deterministic or probabilistic at its core. 50 years after Hawking's 1974 paper, we still don't have final answers. We have better calculations, more sophisticated models, hints from string theory and holography, quantum simulations on superconducting chips, but the complete picture remains out of reach. Recent experiments try to simulate Hawking radiation in labs. 2023 research published in Nature Communications described quantum simulations using superconducting transmon qubits. A chain of 10 qubits with tunable couplers creates an analog black hole on a chip. Quantum walks of quasi-particles in curved space-time simulate gravitational effects near the horizon. Stimulated Hawking radiation is observed. The state tomography measures qubits outside the horizon, showing radiation escaping. Entanglement dynamics are tracked. The entanglement entropy increases as predicted by the quantum effects near the horizon. This isn't real Hawking radiation. It's an analog, but it tests the principles. If the analog system matches theory, it supports the idea that real black holes behave the same way. May 19, 2025, research published by Dr. Zuhair Ahmed at the Center of Excellence for Technology, Quantum, and AI simulated Hawking radiation on IBM's Brisbane quantum computer using an 8-qubit system. The simulation modeled entanglement between a black hole horizon and emitted radiation. Results showed measurement distributions, matching theoretical predictions. Entanglement entropy followed the area law. A clear page curve emerged. Fidelity was high, trace distance was low. This was claimed as the first hardware-verified realization of Hawking's predictions advancing quantum gravity through computational means. Analog experiments in other systems also exist. Bose-Einstein condensates create sonic black holes where sound waves replace light waves. The condensate flows faster than the speed of sound in a region mimicking an event horizon. Phonons. The quanta of sound waves play the role of photons. Stimulated Hawking radiation in the form of phonon emission has been observed. Optical systems using fibers and nonlinear effects create electromagnetic analogs. Fluid dynamics in water tanks can simulate space-time curvature and horizon formation. These analogs all show some version of Hawking radiation emerging from the interplay of quantum mechanics and effective horizons. They support the theoretical framework, but they don't prove Hawking radiation occurs in real astrophysical black holes. The energy scales are different. The gravitational field is different. Quantum gravity might introduce corrections not captured in semi-classical calculations. Until we detect actual Hawking radiation from a real black hole or primordial black hole burst, the theory remains unconfirmed by direct observation. Why does the temperature-inverse relationship matter so much? It explains why small black holes are dangerous and large ones are stable. Imagine creating a microscopic black hole in a particle accelerator. If it has the mass of a few thousand protons, its Schwarzschild radius would be on the order of 10 to the negative 20 meters, far smaller than a proton. The temperature would be enormous, trillions of Kelvin. It would radiate away its mass in a fraction of a second. The radiation would be intense, but the total energy released is just the mass energy of a few thousand protons, equivalent to a few microjoules. Not dangerous. The concern some people had before the LHC turned on was that a stable black hole could be created that would fall to the center of the Earth and consume the planet. The Hawking temperature calculation shows this can't happen. Any black hole small enough to be created by a collider is far too hot to be stable. It evaporates faster than it can accrete matter. Even if it somehow survived long enough to start eating matter, it would need to consume about 1,000,000 trillion particles just to double its mass and have its temperature. Long before that happens, it's gone. The same logic applies to naturally occurring microscopic black holes. If cosmic rays create them when hitting the atmosphere, they evaporate immediately. The final evaporation stage is called the Planck regime. The black hole shrinks to Planck mass and Planck length. These are the fundamental scales where quantum gravity becomes important. Planck length equals the square root of h bar times g divided by ce cubed, about 1.6 times 10 to the negative 35 meters. Planck mass equals the square root of h bar times c divided by g, about 2.2 times 10 to the negative 8 kilograms. At this scale, the black hole radius equals the Compton wavelength of a particle with that mass. Quantum uncertainty in position becomes comparable to the size of the black hole. The concept of a localized horizon breaks down. Space-time geometry fluctuates. General relativity predicts a singularity. Quantum mechanics forbids infinite densities. Something has to give. Presumably, quantum gravity smooths out the singularity. Loop quantum gravity suggests space itself is quantized into discrete units, Planck-sized loops. The singularity becomes a bounce. The black hole might tunnel into a white hole, a time-reversed object that ejects matter. Or it might leave behind a Planck mass remnant, a stable particle that can't evaporate further. Or it might radiate completely into photons and gravitons, leaving nothing. We don't know. Experiments can't reach Planck energies. That's 10 to the 19 giga electron volts. The LHC reaches 10 tera electron volts, 16 orders of magnitude too low. Theoretical consistency suggests complete evaporation. If black holes leave remnants, those remnants can carry information. Infinite types of remnants, one for each possible black hole. Initial state. That violates effective field theory. The vacuum would be unstable. Pair production of remnants would occur everywhere. We don't see that. So most physicists favor complete evaporation with information encoded in correlations in the radiation. But proving that requires a quantum gravity theory that works, and nobody has one yet. String theory is the leading candidate, but it's still not fully formulated. It predicts extra dimensions and supersymmetric particles, none of which have been observed. Loop quantum gravity is an alternative, but it hasn't successfully incorporated matter and forces beyond gravity. Other approaches, like causal dynamical triangulations, asymptotic safety, and emergent gravity exist, but remain less developed. The fundamental problem is that gravity is weak at accessible energy scales. Quantum effects are negligible. We can't test the regime where both matter. Black hole evaporation is one of the few windows we have into quantum gravity. It's purely theoretical, but it's rigorous. The mathematics is solid, even if the final interpretation remains debated. What happens to the radiation after it's emitted? It spreads outward at the speed of light. Over time it redshifts and cools. Eventually it merges with the cosmic background. The information encoded in the correlations becomes impossible to recover, not because it's destroyed, but because it's scrambled beyond any practical reconstruction. This is similar to burning a book. The information isn't destroyed. It's converted into heat and smoke and ashes. The quantum state of all the particles still contains the information in principle. But reconstructing the original book from the smoke particles would require knowing the exact quantum state of every atom. Impossible in practice. Same with black hole radiation. The information is there. Getting it back requires measuring correlations across the entire radiation field with perfect precision. Not feasible. So while information is technically preserved in the quantum state, it's lost for all practical purposes. Some physicists call this effective information loss. Others insist there's a difference between in principle and in practice. The debate continues. The timescales of evaporation also explain why we don't see naked singularities. A singularity is a point where density becomes infinite and physics breaks down. General relativity predicts singularities form inside black holes and at the Big Bang. Roger Penrose proposed the cosmic censorship conjecture. Singularities must be hidden behind event horizons. We can't see them. Naked singularities, where the singularity is visible, would violate causality and predictability. If a black hole evaporates completely, does the singularity become naked at the end? Hawking radiation prevents this. The black hole evaporates away before the horizon shrinks to expose the singularity. The final moments occur at Planck scales where quantum gravity takes over. The singularity presumably doesn't exist in the quantum description. Space-time is smooth or discrete at the smallest scales. No infinite densities. The cosmic censorship is preserved, but this is conjectural. We need the theory. Why care about any of this? Black hole evaporation ties together thermodynamics, quantum mechanics, and gravity. It's a testing ground for fundamental physics. It tells us space-time is dynamic. It tells us quantum mechanics applies to gravity. It tells us information is central to the universe. It tells us the second law of thermodynamics is universal. It tells us the universe has a finite lifetime of structure. All of these are profound insights. Understanding them deepens our grasp of reality. It also has philosophical implications. If black holes evaporate and information is preserved in some form that suggests the universe is fundamentally reversible, the arrow of time emerges from entropy increase, but the underlying laws are time-symmetric. The past and future are encoded in the present quantum state, free will determinism. The nature of time all connect to these questions. If information is truly conserved, maybe the universe is a vast quantum computation. Maybe every event is recorded somewhere in the fabric of space-time. Maybe the holographic principle means our three-dimensional reality is a shadow of information on a distant boundary. These ideas sound like science fiction, but they're taken seriously by leading physicists. The detection of Hawking radiation would be a landmark. It would confirm that black holes are quantum objects, not just classical gravity wells. It would validate semi-classical calculations in a regime we can't otherwise test. It would connect particle physics to cosmology. It would give us experimental access to physics near the Planck scale through primordial black hole bursts if they exist. It would constrain models of the early universe by telling us how many primordial black holes formed. It would probe quantum gravity indirectly. All of that from observing a gamma ray burst with the right signature, so telescopes keep watching. Fermi-Lat T scans the sky for high-energy photons. Faradas Magic Hess and the upcoming CTAO watch for Cherenkov, light from atmospheric showers, triggered by tera-electron-volt gamma rays. Space-based detectors like the proposed Imago will cover intermediate energies. If a primordial black hole dies within detection range, we'll see it. The signal would be unmistakable. A point source flaring in gamma rays with a thermal spectrum, shifting rapidly to higher energies as the hole shrinks, then cutting off abruptly when it's gone. Duration from fractions of a second to minutes, depending on the initial mass. No other astrophysical object produces that signature. What about the recent discovery that everything evaporates? The May 12, 2025 paper showed that objects without horizons, neutron stars, white dwarfs, planets, also emit Hawking-like radiation due to space-time curvature alone. The key insight is that tidal forces from gravity separate virtual particle pairs even far from a black hole. The particles are born apart. One escapes easily. The other is pulled back toward the mass. Energy comes from the gravitational field. The object loses mass. This process is universal but extremely weak. For a neutron star, the luminosity from Hawking-like radiation is about 10 to the negative 30 watts. The sun emits about 10 to the 26 watts. That's 56 orders of magnitude brighter. Measuring Hawking-like radiation from a neutron star is impossible with current technology. But conceptually, it changes our understanding. Evaporation isn't a black hole phenomenon. It's a gravity phenomenon. Anything with mass curves, space-time. Curvature produces radiation, everything decays. On long enough timescales, even a planet evaporates into photons and gravitons and neutrinos. The universe asymptotically approaches a state of maximum entropy and minimum structure. The endpoint is photons, traveling through expanding space forever. The wavelength stretches, the energy decreases, the temperature approaches zero. Entropy approaches a maximum finite value. The story ends. One final twist. The recent findings published February 23, 2025 by Falke Vondrak and Van Swylicom calculated an upper limit to the lifetime of stellar remnants from gravitational pair production. They showed that in an ideal environment with no other effects, a neutron star evaporates in 10 to the 67 years, a white dwarf in 10 to the 78 years. These times are much shorter than previous estimates that assumed only black holes evaporate. The calculation is based on the non-local heat kernel expansion in quantum field theory. The effective action includes an imaginary part encoding particle production. The integrin reduces to the square of the Weyl tensor in Ricci flat spacetime like around a black hole. The Weyl tensor captures tidal forces. Tidal forces separate particles. Particles become real. Mass decreases. The formalism applies to any mass configuration with curvature. The escape fraction depends on geometry. For spherical objects, most radiation is reabsorbed. But some escapes. Over 10 to the 70 years, that's enough to evaporate a star. The universe is decaying much faster than previously thought, though still unimaginably slowly by human standards. The upshot is that given enough time, everything vanishes. The black hole era ends not with black holes evaporating, but with all massive objects evaporating. Then the dark era, then nothing but radiation. The mechanism behind all of this remains one of the strangest in physics. It's not intuitive. It's not something you can visualize easily. It's buried in the mathematics of quantum field theory and general relativity. But the result is clear. Black holes die. They radiate. They evaporate. The process is excruciatingly slow for large holes, blindingly fast for small ones. The temperature is inversely proportional to mass. The evaporation time scales as mass cubed. The entropy is proportional to horizon area. Information is conserved in quantum correlations. The page curve rises, then falls. The paradox has a resolution, at least in certain models. Analog experiments support the theory. Direct detection remains elusive. The final stages involve quantum gravity, which we don't fully understand, but the framework is solid. 50 years after Hawking published his 2-page bombshell, the idea that black holes have temperature and evaporate has become a cornerstone of theoretical physics. It bridges gravity and thermodynamics. It exposes the deep connections between seemingly unrelated areas of physics. It points toward a unified theory. It tells us the universe is finite in structure but infinite in time. It tells us entropy always increases. It tells us information might be fundamental. And it tells us that even the darkest objects in the cosmos, the ultimate gravitational traps that swallow light itself, will one day vanish into a whisper of radiation, leaving nothing behind but a cold, empty, expanding universe. Recent September 29th, 2025 reports from Science Daily confirmed that a fresh black hole merger detection offered the clearest evidence yet for Einstein's relativity and Hawking's predictions. Scientists tracked the complete cosmic collision, confirming that matter and energy obey these fundamental laws even in the most extreme environments. The work continues. New telescopes launch, better detectors come online. Theoretical calculations refine. Quantum computers simulate. Each step brings us closer to the full picture. Maybe we'll detect a primordial black hole burst. Maybe we'll build a quantum gravity theory that works. Maybe we'll discover something entirely unexpected that changes everything. The universe doesn't care about our theories. It does what it does. Our job is to watch, listen, measure, and try to understand. Black hole evaporation is one of the clearest examples of how the universe operates at the boundary between the known and the unknown. It's a place where our best theories collide and force us to think harder. That's where the real physics happens.